So our results today, you can see where that split. It was 8 people thought it was A, 3 thought it was B. I'm glad no one thought C, D, or E. So, if that's the best you can do is narrow it down to A or B, you got a 50-50 shot, which is pretty good. Anyways, we don't need to narrow it down to just 3 or to 2 and do 50-50. We can remember that a type 1 error is whenever you reject the null hypothesis when actually the null hypothesis is true. And frequently we don't know if we've actually committed a type 1 error or not. Sometimes we can find it out. Basically, we figure out what's the probability of a type 1 error. And we're not going to talk about that for this particular problem, but the rejecting the null would mean that the anti-pollution device is effective. We conclude that when in reality, the null hypothesis is correct. It isn't effective. So the answer is A. Okay, so the other one would be the type 2 error. So that's when you fail to reject the null hypothesis when you should. Okay, that's good. All right, actually, this right here, actually, I don't need to say anything about the AP test, but the progress checks, don't forget that those are available. I highly recommend you guys look through those progress checks, especially 6B and 7B, which will relate to Unit 9, and a really good review. Today, we're going to talk about type 2 errors. We already talked about the probability of a type 1 error. Remember, that's just the same as your significance level. So we're going to talk about type 2 errors and power. So this is going to be a good one. Most times the true value of a population is different from the proposed one to some degree, right? If you're saying, I think the true proportion of people in this school who favor X is 30%. If it's 31%, it's off, but you're pretty close, right? Not a big deal. So most of the time it's going to be different. Whether the difference between them is sufficiently large to matter is the purpose of a significance test. So we can reject or fail to reject the null hypothesis as the likely population parameter based on those sample results. And one of the factors that determines whether we reject the null or not is the difference between the true value and the null hypothesis. So where is the actual value? Where is the hypothesized value? If the difference between those two values is really small, we're unlikely to reject the null. If it's really big, we're more likely to reject the null. So just conceptually, that makes sense. So if you said it's 30% and the true value is 70%, that big of a difference, you're likely to reject the null. Okay. Now the difference between these two values is called the effect size. So the bigger your effect size, in the end, the more power your test will have, but we'll talk about what power is. So in this example, we're going to, the red line is going to represent the distribution surrounding the null hypothesis. And the blue line represents the distribution surrounding the true value. With an effect size this big, this is going from 73% to 28% to 45% different. The probability of giving a sample that will cause us to reject the null is practically 100%. Let me explain what I mean. This is a hypothesized distribution of the population. That's what we're testing. In this scenario, we're pretending we know where the true population is. All right, so if I drew a sample from here, I'm going to get maybe a sample from here, 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 just a lot of different samples. And I'm going to end up with some kind of a population, sample mean of proportions. So let's say it ends up right here. No matter where it ends up, no matter where my sample is drawn from, the lowest practical sample mean that I might get is somewhere in this range. And yet, look at how much higher that is than the hypothesized values. And I'll actually draw lines. Here may be a range of possible outcomes. You might get a lot right here, and then it'll spread out a little bit. So no matter what sample results I get, it's likely to be higher than anything in the hypothesized value. So at this point, this would be so extreme that we say, you know what, we're going to reject the null hypothesis. This is not true. Now, we can't say what it actually is, but what we can say, it's not the null hypothesis, the null proportion. Okay, so does that make sense, what we're talking about here? Okay, and in reality, we don't know where the population is. If we did, if we knew where the population was, we wouldn't be doing any hypothesis testing. So this is just to give us some idea of conceptually what's going on. So since there's no overlap between these two distributions, every individual from the population will be greater than the distribution around the null hypothesis. There could be some extreme outliers, but that would be very rare. Now let's look at this example. Same thing going on. I have a hypothesized value, and then I've got the population is sitting right here in blue. There are a lot of individuals that if I picked a sample from over here, it would fall right in line with the null hypothesis. If I picked a lot over here, it might be big enough where I reject the null hypothesis. If it's right in the middle, maybe it's like right on the edge of rejection or not, because the rejection line will be somewhere right there. All right, so it depends on the population, the sample that I draw, whether we reject it or not. So this has a smaller effect size because the difference between the two means is not nearly as big. It's easy to imagine picking a sample from the population that will not give sufficient evidence to reject the null, even though the true population proportion is greater. So what kind of error would that be? If we didn't reject the null, but we should have. There it is, type 2, failing to reject the null, even though we should have. But again, this might be so close that it's not even a big enough gap for us to be able to tell. Now we can talk about ways to make that determination. Okay, so now let's talk about this. And I'm going to take us over to this lovely display. So same thing going on. In fact, you can see I just stole those previous pictures from here. So we're saying that the null hypothesis is that we have a proportion of 33%. The alternative hypothesis is that, in reality, let's say that the real proportion is actually 0.5. So our effect size right here, if I move this down, you can see that changes my distributions, 0.5, like 0.49 and 0.5. And you can see right here, now notice, it's worth looking at it now. These numbers up here at the top, it says the probability of type 1 error, probability of a type 2 error, and the power of the test. And this example is going to help us understand what the power means. So notice, if I increase my effect size over here, my power is 100%, type 2 error is 0, and type 1 is still 5. But anyways, notice how the power and the type 2 error changes. Okay, so let's consider what, I'm going to take this back to where it started, 0.33. So the type 1 error, if we look at this, the type 1 error is our significance level. So let's remember what this means. This represents the whole range of possible outcomes according to the null, right? So if we really think the population lives there, because I need to remind you, we don't ever see this. We don't actually know where the population is. So according to the null hypothesis, we think it really does line up at 0.33. And, you know, if we pick a random group of individuals, you know, we might get any kind of sample results. And then sometimes just by random chance, we're going to fall in this range right here, which is the error of rejecting the null hypothesis, even though it's true. Yeah, it's, and I want to clarify, this is all hypothetical. Okay, because again, we don't know where the population really lives. So hopefully this is not confusing the way I'm describing it. But in this case, we're assuming that the null is true. and that ending up in this range just by random chance, we have a 5% chance of that happening because our significance level is 0.05. All right, so we're ignoring where the true population is because we never know where the true population is. Okay, so let's show this. Here's the probability of a type 2 error. Notice what happens when I move this. Notice where the delineation between type 1 and type 2 is. It's always at the edge of our type 1 error probability. So wherever your type 1 error is, that's going to form the line where anything below that forms type 2 error. And I know right now this doesn't make sense, so let's go back to this. And now we're going to look at, again, we're looking at this conceptually because you're not actually going to ever have access to the population. So let's look at this. In our example, we're saying the true population parameter is 0.5. Our hypothesis is that it's 0.33. So if you're with me on this, true population. Now, this range right here represents all of the sample results we could get that will cause us to fail to reject the null hypothesis. Even though our true population parameter is 0.5, I could get a random sample that gives me all the way down to, like 0.37, right? That could be my sample result. And with that sample result, I would fail to reject the null hypothesis. But I could also get a lot of them up here that, maybe there's a result that this particular sample ends up right there. And then here I would absolutely reject the null hypothesis. So anything to the right, if I clear this, anything to the right of this line means I reject the null hypothesis. Anything to the left means I fail to reject. And since in reality there is a difference between them, this side of the line, failing to reject, represents a type 2 error. This is no error at all. If the population really is different and I reject the null hypothesis, I have done exactly what I'm supposed to. And this is what we call the power of the test. So I'm going to turn this box on real quick. And that green region represents the power of the test. It represents the rest of the area under this curve. So this area of the curve would be where I would draw a sample that would fail to reject the null hypothesis incorrectly. This region to the right of it represents the area where I do reject the null hypothesis correctly. Okay, and I'm going to pause right there. Does that make sense? I'm getting a lot of, it is a lot to process.
That makes sense, but I don't know how much I've booked that.
Okay. So. I'm gonna go through this again, but I'm gonna ask you guys questions along the way. This blue line represents our true population. This red line represents our hypothesized population. Is the true population different from the hypothesized population?
Yes.
Yes, it is. We can see that it's greater. So what do we want to accomplish with our hypothesis test? Do we want to reject the null hypothesis or do we want to fail to reject it?
We want to reject it.
We want to reject the null hypothesis. And the only way we reject the null hypothesis is looking at the red curve right here. Focus on that because that's what we're testing it against. Focused on the red curve, the only way we reject it is if we get a p-value that is greater than our significant, or sorry, that's less than our significance level. So the area under the curve here has to be less than 0.05. And there are a lot of possibilities for this to happen because all of these different sample results under the true population, a lot of them, like this result right here, if this came from my population, I would reject the null hypothesis. This one right here, I would reject the null hypothesis. This one, I would reject the null. All these that I'm drawing, all these cause me to reject the null hypothesis.
Are those just like hypothesized, like population means? Or sample means?
Yeah, these would be different sample means that I drew from the population. And all those lead to us correctly rejecting the null. I could also get a sample that lives right here, or here, or here. And all of these will cause me to fail to reject the null hypothesis because they didn't give me a p-value small enough to reject the null. Maybe I should have done that in a different color. Oh well.
But how come that failing to reject is incorrect?
Because in this case, we actually know that the that the true population is greater than the null hypothesis.
Oh.
And this is all, again, hypothetical, because we're going to be talking about hypothetically, what would a type 2 error be? Hypothetically, what is the probability of it? Though it's hard to know in reality. So all the blue lines that I'm about to draw in here represent your failing to reject the null hypothesis. All the red lines represent you correctly rejected the null hypothesis. It turns out in this case, and here's, I'm going to go back up to these percents at the top. With these particular parameters that plugged in, there is a 20% chance that we are going to fail to reject the null hypothesis. And that means there's an 80% chance that we're going to correctly reject the null hypothesis. And so therefore we end up with a power of 80% and a probability of a type 2 error of 20%. And let me put you at ease real quick if you're worried about this. You never have to calculate type 2 error from scratch. They're either going to give you power or they're going to give you type 2 error if they care about the probabilities. Okay. So I'm going to clear the screen. And what I'm going to do is I'm going to change some of these now. First thing I'm going to do is I'm going to change the significance level. And I'm going to change my significance level up to 10%, that is. And notice how this changed. This line moved over. I'm going to move it back to 5%. There it is. So watch this white line. It went from a 0.05 significance level to a 0.10 significance level. And look at how that changed the areas. The blue area is now smaller. Again, just to show that, there's 5%, there's 10%. The blue area got smaller. In fact, now under this blue curve, there's only 12% of the area would lead to a type 2 error. 88% of the area would lead to the correct rejection of the null hypothesis. So it turns out, yeah.
So what's the result you get?
All right, no worries.
Very good. I was. Spit it out. Dude, I can't. I don't know what I'm trying to do.
I understand.
Even trying to formulate a question.
Here, maybe. I'm trying to think of other ways we could talk about this. And
I understand all the mechanics. That's
sure,
not a problem. But like the
what things represent.
yeah, and like what it means in like a real world.
No, that's a good way of thinking about it. Maybe we can work through this.
I'm seeing problem with
Sure. So let's say, I'm trying to think of just a scenario. I have a hunch that the average, I have not actually paid attention to gas prices in a while. How much does it cost right now for gas? $2.97?
like cheapest.
$2.97. So I have a feeling that the average gas price in America is $2.85. My prediction is that $2.85 is the average because Flagstaff, costs a little more for fuel up here. And some places are really cheap, like everywhere in Texas. So I think the average gas price in America is actually $2.85. Here's what's actually going on. Don't pay attention to these numbers at the bottom, okay? They don't matter. Here's what's really going on. The real gas price in America right now is $3.05. Let's just keep it at nice numbers. $3.05. Okay. Now what I do, I don't know this. I haven't looked at every gas station in America, so I don't really know that's true. But let's say that knowledge exists. Okay. What I do is I go and I sample from lots of random sample across the country. I pull 50, and notice, look, it's 50 is my sample size. I look at 50 random gas stations across America, and I get the average gas price from all those gas stations. And what I end up with from that sample is $2.95. Let's keep it right in the middle, $2.95. So that $2.95 sample mean means I go, let's say that this is where my 295 lives. All right, now this, according to my null hypothesis, right here, according to my null hypothesis, this, let me get rid of the type 2 error in the power. I don't reject my null hypothesis because the only way I reject my null hypothesis, because I'm looking for the probability of getting this result or greater, I end up with a p-value. I'm making up numbers here. Let's say my p-value for this is 0.10. That would be about 10% right there. So at this point, I say I fail to reject the null hypothesis. The gas price really is $2.85. Or we do not have convincing evidence that it's not $2.85. So I just did a random sample of 50. I got $2.95. I didn't reject the null. I said that it's $2.85. Now, what I did here was I committed an error because in reality, it's $3.05 average in America. So what I did was I happened to pick a random sample, and now let me clear a lot of the stuff right here. I picked a random sample that maybe were these values right here, which can happen. Maybe I have a high value, maybe I have a low value, and let's say that's 50 dots, but it tends more toward right there. Now, I didn't get any of the true gas prices that were the high end of the population range. I didn't get very many in the middle. I got most of them kind of at the lower end. And whatever happened here, I did end up with a mean from this sample of 295 randomly.
So each of those dots represents a gas station that you sampled and then their price there.
Yes.
Okay.
Yes. So the dots represents the individuals that are part of my sample. Now, what would have been ideal is to reject the null hypothesis and say it's actually greater than 285. I wouldn't be able to say it's 305, but I could say it's above 285. And the only way I do that is if I get a big enough number so that I can reject the null. And I didn't do that. So within the realm of all the sample outcomes that could have happened in the population, which is shown by this blue line. I could have gotten a sample result that lived here, 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 but I happened to get this one at 295. So from this sample right here, I failed to reject the null hypothesis. And so I'm saying that it costs 285 for gas in the country. And I rejected the 305. Or if that makes sense.
Yeah.
Now, if we keep working with this scenario, what I want to do is, like, let's say that 50, I just got a bunch of gas stations that were on the low end. So now what I'm going to do is I'm going to bump this number up. And notice there was a 20% chance of me getting this error because, that can happen. 1 in 5, that's actually pretty likely. So I only had an 80% chance of getting it right. And that was just the 1 in 5 where it didn't happen. But now I come back and I say, I don't think 50 was a big enough sample size. That's like 1 per state, right? It's exactly 1 per state. We know our math. So I'm going to bump this up and I'm going to say, I want to get at least 4 per state. So I'm going to get a sample size of 200. Okay, and look at what that did. We know that when we get a bigger sampling size, our sampling distributions get smaller and they get narrower. And so now look what happened to our power and our error. Now, if I get 200 gas stations, the probability of me getting 200 gas stations that are all low enough to give me an average of 285, it's incredibly small. They're saying 0. It's not exactly 0, but it's close enough. So my results are most likely going to be here, 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 lots of different places, even down to here, right? Even at the most extreme that I might think likely, it's still going to be above my cutoff point where I choose to reject the null hypothesis. Okay. Yeah. And so now we can think of power this way, because I haven't phrased it this way yet. The power of a test is the probability of correctly rejecting the null. I wanted to reject the null because the true gas price in America is 305. I wanted to reject it. And the power is the probability that I will correctly do so. So in this case, because any outcome below this cutoff point right here is basically not going to happen, my power is 100%. And since I basically can't fail to reject the null hypothesis, I can't fail to reject the null hypothesis, I can't get a type 2 error. Because type 2 is when you fail to reject the null hypothesis incorrectly. It's basically impossible for me to do that. All right, so there are 3 ways that we can make the power of a test bigger. And again, the power is the probability of correctly rejecting the null. So we've seen 2 of them. One way I can do that is by increasing the probability of a type 1 error. Notice if I went down to a 0.005, my power in this test, actually, let me take this back. Let's say we have a sample size of 50. We'll go back to where we started. So at this point, at the lowest possible significance level, 0.005, the power is 49. If I want to increase the power of my test, I can make my significance level higher. I'm going to bump it up to the highest. And now the power of my test jumped from about 50% up to over 90%. Because it's easier for me to reject the null. Does that make sense? And I can say it this way. The easier it is for me to reject the null hypothesis, the harder it is for me to fail to reject it incorrectly. So, yes. And that's how they're related. In fact, let me show you the type 2 error. That'll help it to see. So I'm going to go from the lowest one. Look at my type 2 error probability down to there. So it's not a direct relationship like, oh, this one went up by 5, so that one went down by 5%. It's more complicated, but we can see that the easier it is to reject the null, the harder it is to fail to reject the null. Okay, let me move this back to just a 5% significance level. We've already seen, of course, how raising your sample size can make it higher power because we get a narrower distribution, and therefore it's really hard for us to fail to reject the null hypothesis. Okay, the other thing we can do, well, this isn't something we can change. We can affect the significance level, and we can affect the sample size just by choosing to change those. But this is the other thing we could do. We could actually change our effect size. Remember, the bigger the effect size is, the easier it's going to be to reject it. So notice when I bring this down, this effect size is 0.04. The only way I reject it is by having a huge sample size and by having a big significance level. And look at that. Even with that, with an effect size of 0.04, that's the difference between 0.37 and 0.33. Even with a 0.04 effect size and maximum stuff here, it's still only got a power of 56%. There's about a 50-50 shot. I'm still going to get a type 2 error in this case. Okay, so now let me show you, if I bring this back to 50 and bring that back to 5. So let me make the effect size really big. With that big of an effect size, I speculated as 0.33 is the true population. The real true population is 0.83. With that big of a difference, a 0.5 difference between them, there is no way we're going to fail to reject the null hypothesis. The power is 100%. So a big effect size means that we will have more power in our test. Okay, now I still feel like this might be a bit confusing. So are there any questions on this before we jump away from this? Yes, most likely. Okay. So I'm just showing you different things. Here's the sample size going down really low. Here it's really high. And it's just maybe the thing to think about is the overlap between the true value and the hypothesized value. Here there's no overlap. Here there's a lot of overlap. Here just a crazy amount of overlap. And so therefore, that's going to decrease the power. The more overlap there is, the less power the test has. Okay. So let me go ahead and close this down. So this is what you will have as just a reference if you want to go back to this presentation later. So if we put this in probabilistic terms, the type 1 error is the probability of rejecting the null hypothesis on the condition that the null hypothesis is true. And that's what we find in the red region. Type 2 error is the probability of failing to reject the null hypothesis given that the alternate hypothesis is true. So that's represented by the blue. There is a difference between the true value and the postulated, the hypothesized value, but this blue region represents all of those outcomes where we would fail to reject it. And we end up with an error. The power is the green shaded region. That's the probability of rejecting the null hypothesis on the condition that the alternate hypothesis is true. This is a good outcome. It's not an error. If there is a difference between the null and the true value, we want to reject the null. And here it is. Now it's shown on this. We rejected the null. The alternate is true. That is the power of the test. And there we go. So this is going to be the main thing, and we're going to make a big deal about this in a second. we don't ever calculate type 2 error by looking at distributions and doing complex calculations. We don't do that for power either. We just think of it in terms of the power of a test is 1 minus the probability of a type 2 error. Because this, notice what's going on. The alternate hypothesis is true. That's what we're saying. If we correctly reject it, we get the power of the test. If we fail to reject it, we get the type 2. This combines to represent 100% of the outcomes. Now, and here's what we're saying as far as type 2 error to make sure this is clear. If here's your sampling distribution, or sorry, your hypothesis. So here's P sub naught, or it could be mu sub naught. And then this is your, I'm trying to make this a little bit further to the right. I failed a bit. All right, let's say this is the difference between the two. This is the true value right here that I just put on the right. This is such a small difference that, yes, technically we're committing a type 2 error by not rejecting the null, but sometimes the difference between the two is insignificant. But anyways. Yeah, it's not type 2 error in the sense like we made a big mistake. Yes, it's not exactly the same. So technically we made a type 2 error, but we, there really isn't a significant difference between the two values. Okay, there are only 3 ways we can increase the power of a test. Again, this is for your reference to come back to. I just give the scenarios here, or sorry, the parameters that I started with. So pay attention to the area of the green. This should be the area of the green, whatever. So we can increase sample sizes. I didn't change any of the parameters except for sample size here. Went from 50 to 200, and you can see how the green is a lot more of the area now. Power increased from 0.41 to 0.88 in this case. So the power we started with is 0.41. We can increase the significance level. So in this case, I went back to the original, but then I only changed the significance level from 0.05 to 0.10, and the power increased from 0.41 to 0.56. And then we can increase the effect size. We can't actually change the effect size, but assuming that this can change, if the effect size went from 0.10 to 0.20, the power increased from 0.41 to 0.89. And if I changed all 3, the power increases from 0.41 all the way up to 100% essentially. And again, let's remember power is the probability of correctly rejecting the null hypothesis. Keep in mind that we don't know the true population parameter. So in most cases, we don't really know the probability of a type 2 error and therefore the power. We just need to understand how type 1 and type 2 errors in power are related and how to interpret each one in specific contexts. The only calculation you're going to need to know is this. Power equals 1 minus the probability of a type 2 error. That's it. Okay. So as complicated as it is conceptually, mathematically, we don't do much with it. All right, so here are some questions. And, well, I'll just let you read that for a second and see if you can reason your way through it, even if your head's a little bit like mush right now. So there we go. So yeah, if we think in those, and sometimes thinking in probability terms makes it more confusing, but I think here it can actually help. This is the probability of correctly rejecting the null hypothesis, or rejecting the null on the condition that the alternate is true. The alternate is that the driver is speeding. It was correctly done. So just like Eli said, so if we rejected it, he got a ticket, he was speeding, everything is good. So very good on that. Okay, so similar thing here. We've got doctor uses diagnostic test. Anyways, I'm going to skip down. Here's the alternate and the null hypothesis. You can read those. Which best describes the power of the test? So which one does that align with?
Oh,
Mr. Choices. Oh, okay. No, I mean, that's good to kind of verbalize it first. Okay, there it is. This is the power is the probability that the new test indicates the disease in a patient who has the disease. And that's what we want. So that's it. Now we can go back to some previous problems we had dealing with probability and things like that. When we had to work with complements and stuff. And they were saying that when you get a positive, like 10% of the time, people will test positive who don't have the disease. 5% of the time, people will test negative when they do have the disease. And so that's what we call those false positives and false negatives. Those are really type 1 and type 2 errors that are happening. So a false positive would be you do have the disease, but you really don't. And therefore you rejected the null, even though you shouldn't have. So a false positive would be a type 2. A false negative, I'm sorry, that would be a type 1, because you did reject the null even though you shouldn't have. So a false positive is a type 1. A false negative is a type 2, because we're saying you don't have the disease when really you do. All right. All right, I think there's another one like this. Here we go. Same thing. You have hypotheses. What represents a type 2 error for these hypotheses? So in this case, type 2 error would be failing to reject the null hypothesis when you should have. And this, in this case, we're talking about a false negative. So the doctor says, you don't have arthritis. Really, the person does. So a false negative in this case. And that is correct, the answer there. Okay. Let's see. So we have a one-sided hypothesis test to be performed with a significance level of 0.05. Suppose that the null hypothesis is false. If a significance level of 0.01 were used instead of a significance level of 0.05, which of the following would be true? So read through those and determine how it would change. So I was saying that sometimes it's good to draw a picture here. So I'm going to say this. Here's the null. Here is the hypothesized. Sorry, this is the true value on the right, and the left is the null. So if I went from a 0.05 to a 0.01, that's like moving from here to there. And what I just did is I increased the type 2 probability from there to there. And then conversely, I decreased the power from here to here. All right, so there it is. The probability of a type 2 error is going to increase and the power of the test will decrease. And just keep in mind, by moving from 0.05 to 0.01, we made it harder to reject the null. And a type 2 error is failing to reject the null when we should have.
I swear to God, I knew that.
That's, I believe you. I believe everyone when they say anything.
This is a bandwagon.
Okay, well, we got a new one to redeem yourself. Hopefully Eli messes this one up.
It was the last one I read.
All right.
I don't know.
So there we go. This is the one we did for bell work. This is rejecting the null when we should not have. This is not an effective anti-pollution device, but the scientists said that it was, and therefore made a mistake. That was an error. Okay. Well, this is just a lot of stuff to read. But let's read through this individually and see if you can come up with a good answer for this one. This is a lot to read and to digest, but essentially you're working through what's the full process of this hypothesis test. And what you do have to assume is that the distribution of birthdays is normal. And we have to assume that because one of the assumptions in doing a hypothesis test is that the distribution is normal. And if we don't have more than 30 in our sample size, then we need to assume that the population is normally distributed. Okay, birthday lunch times, because birthdays themselves are uniformly distributed, but birthday lunch times, yeah, let's assume there's a normal distribution. Knowing that there are no outliers in the data, we don't want to have outliers because that can throw out the standard deviation or the standard error in this case, and that can just throw off all of our calculations. So no outliers, that's good. We do want to assume that. Okay, using a t-statistic to carry out the test. So the t-statistic is needed here because we're dealing with means. It's the average number of minutes. So it is a t-statistic, not a z. Using 9 for the degrees of freedom, it's always 1 less than the sample size. So there are 10 randomly selected company employees, so 9 degrees of freedom. The last one is where we make a mistake. If your p-value is greater than 0.05, then we would fail to reject the null hypothesis. And we would conclude, so it's just weirdly stated here, the conclusion is correct. We would conclude that, or at the very least, we don't have convincing evidence that the time is greater than 60 minutes, but we should have failed to reject the null hypothesis, not rejected it. All right, so that is one heck of a employee-focused company right there. So there we go. Let's see what else we have coming up. And you're going to cut it down to 30 minutes and then 15 minutes on their non-birthday? Okay. There we go. This is a pretty straightforward problem. Hopefully this only takes you like less than a minute to read it and come up with an answer. Some of them will be simple. So it's good to see this question. And so a minute ago when I said this was simple, that doesn't mean that it's impossible to make a mistake on it. Just because there's little nuances, you're like, oh wait, what about that? I haven't really considered that ever before. So maybe it's a good thing to see this. And the thing to keep in mind is that we are always testing population parameters. So we're always dealing with mu with our hypotheses. We're never making an inference about a sample because we already have the sample results. We're taking those sample results and making an inference about the population. So we're either saying that the population is 38 minutes or the population is greater than 38 minutes. Not the sample, because we already have our sample results. We're going to know maybe our X bar in this case is 39. So that's going to be known.
X bar would be for the difference of the specific sample, and U is for the whole.
Yeah, X bar is what we have as a given in the problem so that we can calculate the probability and decide whether to reject or fail to reject the null hypothesis. Oh, I didn't erase everything yet. There we go. No, but I'm glad we saw that and we had a chance to kind of clarify that difference. So no worries on that. All right. I think we've already seen some of these before. So we can, here we go. Let's look at this one. Now we've answered some of these. Highway safety engineers test new road signs, hoping that increased reflectivity will make them more visible to drivers. Volunteers drive through a test course with several new and old style designs and rate which kind shows up the best. Is this a one-tailed or two-tailed test?
Isn't it a one-tailed test because we're trying to see that the reflectivity will be more visible? So the increase with the new road sign?
I think that's fair. I think that's fair. Because even if they are different and the new ones are worse, we don't care about, I mean, we wouldn't want to conclude like, oh, let's go with these because they're worse than the old ones, right? So I think it's fair to go with a one-tailed test. Okay, in this context, what would a type 1 error be?
Wait, so is the null hypothesis that the signs like the reflectivity hasn't changed or is the same?
Yep.
Okay.
So same reflectivity. And this is where you might find it, activity, there we go. You might find it helpful to actually write out the null and the alternative hypothesis for these. So the alternative would be the new one's more reflective. New is more reflective. Now it's easier to think about rejecting the null if you know what the null and the alternate are. So looking at this, what would a type 1 error be? There it is. We conclude that the new one's more reflective when really it's not. We did reject the null. What's that? When you shouldn't have. Yeah. Now, I guess this is kind of an innocuous situation because if we rejected it, and it's probably not less reflective. So it's probably okay. But still, it is a type 1 error. Type 2 error would be what?
Saying that they have the same amount of reflectivity when they've actually not.
There it is. If you fail to reject the null, if you say that they have the same reflectivity, when really the new ones are actually better, then that would be a mistake. What is the power of the test?
Saying they've gotten better and they actually have.
There you go. Concluding that the alternate is true and is actually true. The new is more reflective, and that's true. Okay. If the hypothesis is tested at the 1% level of significance instead of 5%, how will this affect the power of the test? Will the power go up or go down?
Down.
Power will go down. If it's harder to reject the null, then it's easier to fail to reject the null. It's easier to get a type 2 error, and therefore we have a lower power. So there we go. Engineers hope to base their decision on the reactions of 50 drivers, but time and budget constraints may force them to cut back to 20. How will this affect the power of the test? It will decrease the power. How do we know? Do you have anything to add? And you're right. It would decrease the power. So if it was a multiple choice question, you could probably find a good answer for it. If it's an FRQ, you'd have to give a little bit more reasoning. Okay, that's no worries. Here, we can look at this real quick. Let's say that we originally would have had something like this. So let's say that this is the true on the right, and this is our null hypothesis on the right, on the left, gosh. So if this was a sample size of 50, if it's 20, the data is going to be spread out more, and there's going to be more overlap. Okay, and that wasn't drawn very well. Let me try that again. I don't know how much better that was, but anyways, with the, I wanted this to be wider. Third time's a charm. I'm gonna make it really wide. There we go. This is gonna look good. Okay, so now this extra overlap with sample size of 20 means this overlap area here's our type 1 error, the significance level cutoff that I just drew in. So this is the power of a 4, including that. This is the power now. Does it look like we've decreased the area? The area under the curve, that is. Okay, we went from over 50%. Here's the 50% cutoff. We went from well over 50% to just about 50%, because now we're going to say we're right at that 50%. So I would say in the second case, hypothetically, we're at 50% power. In the previous one, we were 80% power. I don't know. So more overlap between the two distributions means it is harder to reject the null. Okay. Let's see here. I'm trying to figure out if we need to see more. You know what? Let's just talk through this one. I don't want to. Maybe we can do this one pretty quickly. You're in charge of a shipping company, shipping computers to customers. You learned that faulty disk drive was put into some machines, but there's a simple test you can perform. It's not perfect. All but 4% of the time, a good disk drive passes the test. But unfortunately, 35% of the bad disk drives pass the test too. You have decided on the basis of one test whether the disk drive is good or bad. Make this a hypothesis test. What are the null and alternative hypotheses? Okay, the null is that, would the null be that it's a good drive?
It'd be that it's not bad.
Yeah, I mean, it's not, I mean, good is not bad. In this case, that terminology is fine. I think that's fair. The null, we would assume every drive that comes through meets quality standards, right? That could be the null. Derive. Alternate hypothesis is that it's a bad drive. So this, of course, would mean passing this one test means it's a good drive. Failing to pass it would make it a bad drive. Okay, now let's kind of consider this question right here. All but 4% of the time, a good drive passes the test. So what error is made 4% of the time? Did we reject the null in this case? 4% of the time, did we reject the null?
No, we failed. Right?
We rejected the null.
Wait a second. But we're saying it's a good drive, so isn't that bad?
This is saying it's actually a good drive, and it passes 96% of the time, but 4% of the time it doesn't pass. So what we do is we reject the null. We say it's bad, even though it's actually
you're
good.
saying the 4% is rejected.
Yeah, 4% is rejected.
Oh, I thought, I see.
So it's good to think in these terms. If we know that 4% of the time we're going to get a type 1 error. Now it says here, unfortunately, 35% of the bad disk drives pass the test too. What kind of error is made with that? Yeah, it'd have to be, we failed to reject the null, even though we should have. So this next one represents type 2. All right. So now we already wrote our hypotheses. Given that a computer fails the test, what would you decide? Would you conclude? I mean, what would you have to conclude? Yeah, I mean, we have a test. It failed the test, it's bad. So if it passes the test, we'd have to conclude it's good. All right, I mean, I feel like that's what. Now we will do a calculation in a second. How large is the alpha for this test? 0.04. because your alpha is the same as your probability of a type 1 error. Okay. What's the power of this test? And here we're going to say like the bad drive is actually bad. That is what it would be conceptually. What would it be numerically? There we go. The power is going to equal 1 minus the probability, 1 minus the probability of type 2. So in this case, it's 1 minus 0.35, 0.65. So that's as difficult as it gets mathematically, but getting to that point is not necessarily straightforward. Okay. Are you guys feeling a little better about power type 1 and type 2? Okay. There might still be some confusion on this. Your best bet as far as preparing for the test is going to be going through the progress checks, doing the homeworks that I assigned to get more practice with the running through the hypothesis test for means and for proportions. I know we didn't do any practice ones of those today. So any old homework assignments that have those available, get some practice with it. And if you come to class tomorrow and you are super, super confused, don't worry if you need to stick around and go through a bunch of problems. And actually, here's what I might suggest if you're worried about the test tomorrow. Look at the progress checks. And if half of the problems are ones that you don't feel confident answering, just flag those. Come to class tomorrow, and we'll go through all of those problems tomorrow in class. If you have homework problems that you're looking through from the textbook and you want to look through those, then we'll go through those as well. So that's where we're at. And if you have any questions for right now, please feel free to stick around. Otherwise, you can have yourself a wonderful day.